Last class, we talked about some stuff. Some of that stuff included types of crystalline solids, so solids that form crystals. And there were 3 types of crystalline solids. Crystalline solids, remember, have a well-ordered array of atoms or molecules. So if you zoomed in at their smallest level, you'd see repeating patterns over and over. The opposite of that, or the other side of the coin, is amorphous solids, where if you zoomed in to their tiniest little level, you wouldn't see repeating patterns. So they're a little bit more chaotic. And our crystalline solids, we divided into 3 categories. Our 3 categories are molecular, ionic, and atomic, which are made up of molecules, ionic compounds, and atoms, as one might expect. But nobody took my bait last time in answering what those were. Molecular solids made up of molecules tend to have low to moderately low melting points. These are held together by the 3 types of intermolecular forces that we've previously learned about. So things like dispersion forces, which everything has. Things like dipole-dipole forces, forces between 2 dipoles. Polar molecules have dipoles, so polar molecules have dipole-dipole forces. And then hydrogen bonding, which, remember, is a type of special dipole-dipole force that's hydrogen bonded to fluorine, oxygen, or nitrogen directly. And that can interact with another molecule, and that forms what's called the hydrogen bond, which we learned about previously. Ionic compounds tend to have very high melting points, particularly compared to our molecular compounds. We have full positive and negative charges, sometimes multiple positive, multiple negative charges. So these are much, much stronger because of these full positive and negative forces. And so things like sodium chloride melt at hundreds of degrees Celsius. 800 degrees Celsius should be over 1,000 degrees Fahrenheit. So your oven's not going to even get close. Good luck trying to melt sodium chloride at home. And then we have atomic solids. And atomic solids have their smallest unit made up of individual atoms. So things like diamond, iron, solid xenon, other such things where it's just one of that thing. And we can actually divide these into 3 categories, and their melting points vary quite widely. So our first type of atomic solid is covalent atomic solids. These are held together by covalent bonds where they're sharing their valence electrons. Diamond is a great example of this. Diamonds, of course, are crystalline. That's why they look so pretty. And they reflect light so well. Also because of the way that we cut them. And so diamonds are just carbon bonded to carbon in some array. I don't know what that array is, but it's lots of carbons. It's only carbon, ideally. There's usually some inclusions in real diamonds, but the diamond itself is just carbon. And they're held together by covalent bonds. It's basically a giant molecule, and they have very, very high melting points. So diamond, for example, is estimated to melt at like 3,800 degrees Celsius. So more than 4 times the temperature of sodium chloride's melting point. So in diamond, here's a diamond in the rough. And then here's the crystal structure of a diamond. So this would be one of the repeating units. You don't need to know that that's what that is. But we can see these purple dots are just kind of the corners of our cell that repeats in 3 dimensions. And then each of these dots represents one of the carbons. So it's just this repeating lattice of carbon. Just punch those building blocks in over and over again. And that's what our diamond would look like. So that's our covalent atomic solids, ones that are held together by covalent bonds. Then we've got ones that aren't held together by covalent bonds. These are non-bonding. No bonds formed. And this is stuff like solid xenon and our other noble gases. They don't form any bonds. They just sit next to each other. And they interact with dispersion forces. So solid xenon example here. Xenon atoms have stable electron configurations, and so they're not going to form covalent bonds with each other. So they're just going to hang out next to each other. If they're really cold, then they're sticky enough. They've got strong enough dispersion forces that they'll hold together. But xenon melts at negative 112 degrees Celsius, which is dangerously cold for us. So that's a very, very low melting point. Since they're held together only by dispersion forces, and dispersion forces are very weak. Weak intermolecular forces means low melting and boiling points. And then our last group of atomic solids is our metallic atomic solids. These are held together by metallic bonds, and metallic bonds are the bonds that what sort of things have? Any guesses? What kind of elements? Yeah, you're right. It's metals. So metals can form metallic bonds. And this is sort of similar to our non-bonding atomic solids. We sort of think of them as just hanging out next to each other. But they're not just hanging out, they're also passing around electrons. So they're passing around, sharing their electrons. And our model, or most basic model for these atomic solids, is that it's positively charged ions, for example, like Fe2+, all hanging out, and there's just a free-flowing sea of electrons that they're sharing. And that free-flowing sea of electrons is why they conduct electricity, for example. Metallic atomic solids have variable melting points because we've got things like mercury that is a liquid at room temperature. It melts at negative 39 degrees Celsius. Other things like iron, iridium, titanium have much higher melting points, more in the 2,000 degrees Celsius range. Questions about any of our three atomic solids? So we've got one that's high, one that's low, and one that's kind of all over the place. This is all great flashcard material, by the way. This is what our example of a metallic atomic solid might look like. So we've got all of these cations, the metal cores, kind of sitting around next to each other, and their electrons just kind of float around in between them. Metallic atomic solids are the communists of the atomic world, freely sharing their electrons. Our electrons, right? Hammer and sickle, music plays. All right, let's try identifying these crystalline solids. Identify them as molecular, ionic, or atomic. And compare with your neighbor. All right, first up, NH3. We want to identify this, if it's a solid, as a molecular, ionic, or atomic crystalline solid. What kind of thing, what kind of compound is NH3? Is it a molecule? Is it an ion or an ionic compound? Or is it an atom? Is it an atom? What sort of things are atoms? Gestures at our periodic table. These are where all of our atoms are found, right? So if it's one of these, if it's one of them, then it's an atom. We have two of them, right? We have N and H, and so it's a compound. So it's not atomic. So we can rule out atomic. Not atomic. So then our options are molecular and ionic. Who remembers what our definition for ionic is? What sort of things make up ionic compounds? Awkward silence ensues. It is molecular. This one is molecular. The things that make up Ionic compounds are ions. And we know that something is ionic because it has a metal and nonmetal. Right? So we know it's molecular because it's all nonmetals. Nitrogen's a nonmetal, or nonmetals live in that upper right corner of our periodic table, the one that we have in the class has a little stairway. So generally things up and to the right of that are nonmetals, and hydrogen also typically gets lumped in with nonmetals. And since we've got only nonmetals, that makes this molecular. So that's how we know it's a molecular solid. And then next up, we've got runs batted in, RBI. A little MLB humor for you there. So RBI, what do we have for rubidium iodide? What kind of compound is that? Do we have one element symbol? No, we have more than one element symbol. We've got two element symbols. What kind of thing, what kind of element is Rb, rubidium? We find rubidium, not guilty, but in group 1. And group 1 is metals. It's our alkali metals. And so rubidium being a metal and iodine not being a metal means that we've got a metal and a nonmetal. Metal plus nonmetal equals ionic compound. So this is an ionic crystalline solid. And then last, we've got Kr. That's not Korea, that's krypton. What kind of thing is krypton? It's atomic, because it's just one symbol. So it's atomic, and then what kind of atomic crystalline solid is it? Is it non-bonding, covalent bonding? Is it a metal? Any guesses? Look at where krypton is, find it. Do we think that it's going to want to bond? No, it has 8 valence electrons. It does not want to bond. This is a non-bonding subtype. Questions about how much fun we're having? All right, at least one person's having a lot of fun, and it might be me. All right, so we've talked about some of our intermolecular forces. We're going to now go into discussing some of our states of matter. So in gases, the gas state of matter, molecules and atoms are separated by large distances. This was one of the key points in our kinetic molecular theory. There's big empty gaps of space between our molecules or atoms or whatever other compound we might have. In solids and liquids, molecules or atoms are touchingly close. And this touchingly close just means that they can interact by intermolecular forces. They're bumping elbows with their neighbors. They're not 500 feet away from their neighbors. It's reach out and touch somebody sort of distance. The difference between solids and liquids is in the freedom of movement of the molecules or atoms. So in our liquids, the atoms and molecules are free to move around each other. And that's why liquids can run. That's why when you pour a liquid on your table, like you do every night, when you pour the liquid on your table, it just spreads all over your table, and now your table's wet, if it was water that you poured on your table. In solids, if you pour solids onto your table, first of all, you wouldn't be pouring them, probably, but if you pour them onto your table, they're just kind of going to sit there unless they're, spherically shaped, and then they might roll everywhere. But they don't run in the same way that liquids do. So atoms or molecules are fixed in their positions. And so the analogies that I've used for these is that solids is like the atoms and the molecules are like people at the movie theater, especially if it's opening night and it's a popular movie. All the seats are filled. people are generally sitting in their seats. It's also like all of you for the most part. You're sitting in your seats. You can still move around. Hopefully you're taking notes. Hopefully you're nodding along. Hopefully you're breathing. And you're stuck in your spot. You're generally not swapping positions with your neighbor. In liquids, this is when you would be free to move around each other. So that would be like if I told you all to jump up and swap places or go share ghost stories with somebody else in the classroom. Or more like in a lab setting. There's still empty space, but it's not like a ton of empty space. So you can move around freely. You're not stuck in your seat. Here's a visual of what our gas, liquid, and solid states look like. So solid state, they're all touchingly close. The molecules of oxygen, O2, are interacting with each other. They're kind of locked in their places. They would still be vibrating around. They're kind of stuck there. In a liquid state, they're a little bit more mobile. They're moving around. They're still touchingly close. They're still close enough that they can interact and they can move past each other. And then in our gas phase, there's big empty space between them. And they can also move freely around each other. That's why smells tend to get around in a room. Our gases, as a reminder, have low density in comparison to liquids and solids. This is because of the empty space. Empty space has no mass because it's empty space. They also have indefinite shape, and they assume the shape of their container. They'll spread out until the smell or gas is evenly distributed throughout the room for the most part. They also have indefinite volume, meaning that you can compress them again because of the empty space. Generally, gases tend to have weak intermolecular forces relative to thermal energy. Intermolecular forces is like a stickiness force. If they were really sticky, they'd get stuck together. Since they're not very sticky, they don't get stuck together. Things that are really sticky, you can still separate. It's just sometimes harder to separate. So weak intermolecular forces means they're not very sticky. They probably have dispersion forces. They maybe have dipole-dipole forces, but they have weak intermolecular forces. Our liquids, on the other hand, have high density in comparison to gases because the particles are touchingly close. They're close enough that they can interact. There's no empty space between them. They do have indefinite shape, like we talked about. They'll assume the shape of their container, but they do have a definite volume. You cannot, at least easily, compress a liquid. If you try squeezing a completely full water bottle, like even one of those cheap $1 plastic water bottles, if you squeeze it hard enough, the plastic will just break. It's not going to really get any smaller. It'll just keep changing shapes. Because these are touchingly close, they have moderate intermolecular forces. They have enough intermolecular forces that they can't get away from their neighbor. This is sort of like family sometimes, right? You can't really escape them because of those connections that you have with them. Not to say that you can't escape family, but it is the strongest force in the Fast and Furious universe. So these are sticky enough. They can't escape their neighbor. But not so sticky that they're stuck in their place. Free to move around, but still have to be touchingly close to their neighbor. And so things like liquid water would be an example of course, a liquid. And liquid water has really strong hydrogen bonding. It's not just dispersion, it's got dipole-dipole, and it's got hydrogen bonding, and so it's a liquid at room temperature. Then solids also have high density in comparison to gases for this same touchingly close proximity. They're packed in as tight as they can be. These have definite shape. There's not enough energy for them to move past each other. So this makes solids special. Like liquids, they also have a definite volume, and they can be either crystalline or amorphous, as we had previously discussed. These also tend to have strong intermolecular forces relative to thermal energy. They're stronger / stickier than liquids. The relative to thermal energy part in here, why did I put two Ds? The relative to thermal energy part means just like you could always ramp up the temperature enough that they would all be gases. You could also cool them down enough that they would all be solids. So think room temperature, or if they're all at the same temperature. There should be a picture here. Because molecules in liquid are free to move around each other, they can flow and assume the shape of their container. In solids, though, the molecules are fixed in place, so we've got a representation of what one form of ice might look like. We've got our oxygens in red, our hydrogens in white. So they will generally lock up, the water molecules lock up in a specific pattern, and they can still vibrate in place, just like you all are doing stuff in your place, but they're not going to be swapping spots with their neighbor. There's no do-si-doing and the like, because it's a solid. Questions about solids, liquids, gases? Yes?
What would you classify oobleck? Like a liquid or a solid? I'm very curious.
I'm not 100% sure that I know what the thing is that you're talking about, but I'm guessing that it's either a liquid or it's a suspension of solids in a liquid. It's like if you slap it, it's really hard, or like you can like run on it, but if you stand on it, you sink into it. Yeah, that's a non-Newtonian fluid.
Okay.
I think is what those are kind of generally classified as. So it's a liquid, but it's got special behavior.
Okay.
Yeah. Any other questions? All right. So intermolecular forces give us a couple of special properties: surface tension and viscosity, to name two. If we didn't have any intermolecular forces, by the way, if atoms and molecules weren't sticky at all, solids and liquids would not exist. We would not exist. The whole world, the whole universe would just be gases, which is fun. In liquids, specifically, we can get the effects of surface tension and viscosity thanks to intermolecular forces. So you might know, maybe you weren't aware of this, you can get a paper clip and it'll float on the surface of water if you set it down carefully enough. You can also do this with like a needle. So there's like a trick where you can make a compass where you like hit a needle pointing in a certain direction and then you set it on the surface of water and it'll like rotate and act like a compass. Not a very effective compass for traveling, but it might give you the correct directions. This paperclip is held up by surface tension. So surface tension is also the reason that when you fill up a glass of water all the way, right, we fill it all the way up with water, and then, oops, we added a little bit extra water. You get that little bubble that can form at the top. And you're like, why is the water staying in the glass when it's clearly over the top of the glass? And that's because of surface tension, the same thing that we're seeing here. So this is something that you can try at home. And I believe it would even be safe. Just don't, I don't know. It could be unsafe, but probably not. So this is held up by surface tension. Surface tension, our definition is the tendency of liquids to minimize their surface area. If you tried this on gasoline, which I don't recommend, because you shouldn't have cups of gasoline around your house. But if you tried it on gasoline, gasoline has much weaker intermolecular forces, and so your paperclip would probably just sink into the gasoline, and then you would want to retrieve it with like a magnet on a piece of twine or something, instead of reaching your hand into the gasoline, because that's also bad for you. So try it with water, don't try it with gasoline, just take my word for it. Trust me, bro. Or you could try it with like nail polish remover. That would probably be safe. Still flammable, but less bad for you. Surface tension is also the reason that some insects and creepy crawlies can float on the surface of water, like our good friend here, this mosquito. Hopefully a male mosquito, so it's not going to bite us. So surface molecules, we've got molecules here in blue, because water's, we picture as blue. So we've got water molecules represented as these dots. And if we're on the inside the liquid, right, it's being pulled up, it's being pulled to the sides, it's being pulled down, probably some forward, there's some backwards. It's all directions, 360 degrees of getting pulled on, yanked every which way. Sometimes how it feels at a family gathering when all the aunts and uncles are asking you all your questions and why aren't you getting married yet? Versus these ones up here at the surface. These molecules up at the surface are not being pulled up. They're just being pulled around and down. Since they're not getting pulled up, there's nothing to cancel out that pull down, right? And so they're just getting pulled down by their family, relatable sometimes. They're getting just pulled down, and that's going to suck the surface molecules in slightly, and that's the surface tension. That tension of being held back, held down by the atoms, molecules around you. So these experience a net pull in/down versus something on the inside is pulled every direction and so it's just no net pull. All the pulling forces cancel out. So surface tension kind of firms up, sort of, the surface of the water because of those molecules being pulled down. It's also the reason that water drops are spherical. So we can get pretty pictures of water drops like this, or if you're in space, on the International Space Station, you can get big globs of water that float around because they're not being pulled down and the intermolecular forces just kind of pull them together. So that's a very fun and cool picture. And that's thanks to surface tension. You would not be able to do this, I assume, with gasoline, or at least it wouldn't work nearly as well. It would also be significantly more dangerous because I don't think gasoline flying around the International Space Station is a good idea. I'm sure the water is even dangerous. So that's one of our forces that we have thanks to intermolecular forces. We also have viscosity. Viscosity is the resistance of a liquid to flow. You can also think of it as the thickness of a liquid. This is also thanks to intermolecular forces. So liquids that are viscous flow more slowly, or flow more slowly than liquids that are not viscous or less viscous. So motor oil is more viscous than gasoline. Honey and other syrups and things are more viscous than water. Viscosity increases with intermolecular forces. And surface tension also increases with intermolecular forces. So stronger intermolecular forces means higher viscosity. Stronger intermolecular forces also means stronger or higher surface tension. So if you spill water on a countertop or a table or a surface that doesn't absorb it, it tends to form up into nice little droplets, like on your windshield when you drive in the rain, if you drive in the rain. If you spill something like nail polish remover or alcohol, it doesn't form nice, neat droplets in the same way. And the reason that viscosity is greater in substances with strong intermolecular forces is because now their interactions with their neighbors are stronger, and so it's harder for them to move. They can't move around each other as freely, and so they flow less easily. So honey is a great example. Honey tends to be very viscous. What happens if you heat up honey? Does it flow faster or slower? It flows faster. When you heat it up, you give it more energy, and so then the molecules can move more because they've got more energy to get away from their neighbors. Increasing temperature decreases viscosity. So hot honey runs faster than cold honey. There's also a fun experiment that you can do that you can maybe try out. You can probably, I'm not going to say definitely that you can, but you can probably tell the difference between somebody pouring hot water versus somebody pouring cold water just based on the sound, which is really wild. And that's because of the difference in viscosity. The way that hot water sounds when it's crashing into hot water sounds different than cold water crashing into cold water. So if you have a moment sometime and you're feeling like doing a weird science experiment, try get some hot water, get some cold water, and have somebody pour them for you and see if you can guess which one they're pouring. That's a fun little nothing burger, as they might say. It doesn't help you in any way, it's just cool. So some of our changes between states of matter are melting, freezing, and sublimation. Before we get into those, do we have any questions? So melting, freezing, and sublimation all involve solids. As the temperature of a solid increases, remember that in a solid you're stuck in your place. As the energy in the classroom increases, you grow closer and closer to rising up and taking back your grades and revolting. In a solid, as the temperature increases, the thermal energy causes molecules and atoms to vibrate faster. As they vibrate faster and faster, it doesn't change the bonds that they have with their neighbors. They're still the same amount of stickiness. They just have more energy, and eventually they move too far, too fast for the bonds with their energy, with their neighbor, and they reach their melting point. Reminder that melting is solid going to a liquid. Once you get enough energy, they can move past their neighbors, they can move around their neighbors. Solids are stationary. Liquids move around each other. We're thinking of the atoms or the molecules that make up these substances. So you get enough energy, and now they can move past each other. And so it moves from a solid to a liquid. The opposite of melting is freezing, which we'll talk about soon. So melting, when ice melts, water molecules can break free from their solid structure and they become a liquid. And we've got a fun fact. As long as ice and water are both present, the temperature will be 0 degrees Celsius, assuming that it's well mixed. Always 0 degrees Celsius. If you've got the solid and the liquid, the temperature is the melting temperature, as long as it's well mixed. So a practical application of this, some people only drink ice water if they can help it. Ice water is the way to go for them. There's always got to be ice in the water. It's got to be freezing, frigid, cool. What that means for you is that you are getting a very consistent experience. Your water is always going to be about the same temperature, assuming that you mix it well enough. So you are drinking about 0 degrees Celsius water, 32 degrees Fahrenheit water, which is a very consistent experience. Others of us live on the wild side, and we drink room temperature water. And when you're drinking room temperature water, you are not getting the same temperature every single time. It's the Wild West. It could be 30 degrees, probably not. It could be 35 degrees in Fahrenheit. It could be 70 degrees Fahrenheit. It could be even warm water, God forbid. So if you're drinking ice water, it's going to be a nice, consistent experience, which is fun. And here's that fun fact again, a mixture of water and ice will always have a temperature of 0 degrees Celsius at 1 atmosphere of pressure. Only after all the ice has melted will it get raised past 0 degrees Celsius. Again, we're assuming perfectly good mixing. Once your ice has melted, now you've entered the Wild West. Your water may no longer be 0 degrees Celsius. The same is true for any other drink, like if it's a water-based drink. We have another process that's going from a solid to a different state. We have sublimation. Sublimation is solid straight to gas. We do not interact with the liquid phase at all. And this is happening all the time. Sublimation is happening all the time. We typically don't notice it. The one chemical that you've probably seen, maybe have seen, that does this is dry ice. Dry ice, which you can buy if you're 18, I think is how old you have to be. You can buy it at the grocery store, depending on which grocery store you go to, is just solid carbon dioxide. Since it's solid carbon dioxide, maybe don't play around with it in a small closed room, because that would be bad for you. Solid carbon dioxide at atmospheric pressure does not melt. It never turns into a liquid. It jumps past the liquid state directly into the gas state at the very low temperature of negative 78 degrees Celsius. And sublimation can happen for things that can melt as well. Here's a picture that somebody took. They've got some dry ice in the bowl. Presumably they added some water and now it's frothing and foaming and pouring out this water vapor and CO2. You can also do fun stuff with dry ice with like food presentation. Fancy restaurants sometimes put a little bit of dry ice in a thing and then they pour some water and then it's like you've got a little smoke machine, but you can eat the stuff that's touched by the smoke machine. It's not bad for you. Sublimation will also occur with regular ice and with other solids. Regular ice, wet ice, water ice, also sublimes at temperatures. And this happens below 0 degrees Celsius. So in places where it never gets above 0 degrees Celsius, if there's no new snow that's deposited, eventually the ice will sublime, the snow will just evaporate and be gone if there's not any new snow that's brought in. So this is why ice or snow can disappear even if your temperature is below 0 degrees Celsius. This also is why if you've ever had ice cube trays in your freezer and you leave them in there for a while and then you come back and you're like, oh, I would like a perfectly normal looking ice cube, please. And then you go and look at your ice cube and you're like, these are the freakiest ice cubes I've ever seen. They've pulled away from the side of their container. They're all small and shriveled up. Shrinkflation. No, it's sublimation. So if you leave ice cubes in the freezer for a long time, they get smaller. So that's why they pull away from the sides of their container. You do actually have to swap out your ice cubes every now and then. And what's happening is that the ice cubes, they sublime. They went from the solid to the gas state, and then they probably hit something like the walls of your freezer, or if you had them in a container, they hit the side of the container and they turn back into ice crystals there. And that's why you get all that ice buildup in your freezer. Ice also sublimes out of frozen foods. So if you buy frozen foods and you leave them in the freezer for too long, the ice, the water, sublimes out of frozen foods. So you might open up a pack of frozen vegetables and you see there's ice crystals all over the packaging. That's the water that was in your vegetables. Now it's on the side of the container. It's no longer in your vegetables, and that's why your vegetables are going to feel weird. Those ice crystals came out. They redeposited on the surface of the bag. Food that is frozen for too long becomes dried out. This is freezer burn. So yes, you can store stuff in your freezer for really long periods of time. However, if you do that for too long, you get freezer burn. It's going to come out with really weird textures, especially vegetables are weird if you do it this way. You can avoid this by freezing foods colder than 0 degrees Celsius or whatever your freezer's set to, which is deep freezing. So if you've got stuff that you're going to be holding for a long time, like if you've got somebody in your family that hunts and you're getting, whole carcass of deer or something, you probably invest in a deep freezer so that you can keep it for long periods of time and it stays good. Colder temperature slows sublimation. Things that aren't water, ice, also sublime. So like solid metal also sublimes. It's just a lot slower than things like water. There's also another phenomenon that's very important that I'd like to talk to you about today. How many of you have had ice cream? Ice cream enjoyers in the room? You get some ice cream from the store. You put your ice cream in the fridge. You maybe have a couple of scoops because it's good for your health. You leave it in the freezer. You forget about it. You come back a week or two later. You open it up. You look at the lid. Ice crystals. Devastating. That is also ice that has come out of your ice cream and is now on the lid of your ice cream container. So your ice cream is going to taste kind of funky. If you've ever forgotten about ice cream and it's in the freezer for like 2 months, 3 months, a long period of time, and you go to eat it and you're like, it is ice cream, but I don't like it, right? That is also caused by sublimation. And so the big takeaway, the important takeaway here is eat your ice cream. Don't let it go bad. Eat your ice cream while it's still good. Don't forget about it. If you have ice cream at home, don't forget to eat it. That's the big takeaway from this slide. Arguably. Any questions about melting, freezing, sublimation? Okay, we also have boiling, evaporation, and condensation. So evaporation or vaporization is the physical change from a liquid to a gas. There are a couple of things that affect the rate of vaporization. So some things evaporate faster than others. Rate of vaporization increases. So if you've got a puddle of liquid, it'll evaporate faster if you increase the surface area. So if you spread it out more, then that will increase your rate of vaporization. If you increase temperature, right, heating it up will also increase that rate of vaporization. And then one that you can't really directly involve yourself with is decreasing the strength of intermolecular forces. So for example, water tends to have relatively strong intermolecular forces, IMF, versus acetone, hand sanitizer, nail polish remover, tends to have weak intermolecular forces. They both evaporate and they both cause a cooling effect, but because water has strong intermolecular forces, it evaporates more slowly, it's less of a cooling effect. Things like acetone and hand sanitizer, you feel your hands get really cold when you touch it because it's evaporating so rapidly. Big bracket and some arrows. Liquids that evaporate easily or quickly we call volatile. Ones that don't evaporate easily are termed non-volatile. I think the reference state here is water. So comparing things to water, if it evaporates more easily than water, it's volatile. Acetone, hand sanitizer. If it doesn't evaporate as easily as water, we'd call it non-volatile. Things like oil and other oils. I can't think of a thing that's not an oil. It's like motor oil, canola oil, extra virgin olive oil. Okay, evaporation. Here's evaporation. We've got, down below here, we've got a liquid, presumably water. We know that the molecules that are at the surface are held less tightly than those on the interior. We talked about this with surface tension. So the liquid molecules that are on the surface are held sideways and down. When they're below the surface, they're held in all directions, right? Yes, they're held in all directions. Thank you. And because of that, it's harder for them to break away because they're held in all directions. If you're at the surface, though, you're only held by things that are next to you or below you. And so it's possible, because these are all randomly bumping around, it's possible, and this happens all the time, by the way, that these molecules that are on the surface could just randomly get bumped a couple of times all at the same time, and boom, now they've got a ton of energy and they blast off. They evaporate. Evaporate because they randomly get a bunch of energy. Bunch of energy. Again, just because they got the correct combination of getting bumped by their neighbors, boom, they've got a bunch of energy, they evaporate. And when they evaporate, they have a bunch of extra energy. They're taking that energy from the liquid that they were in. And that's why we've got the thermostat here, the thermometer with the temperature going down. They're stealing extra energy. They're taking energy from everyone around them. They're taken off, and now the liquid no longer has that energy. And that's why evaporation causes cooling. So it's taking extra heat away, and that causes the thing that it's on or in to cool down. If you're at a given temperature, a sample of molecules or atoms is going to have a distribution of kinetic energies. And here's one of my favorite graphs. So in this graph, our x-axis here is energy, so things on the left are low energy, things on the right are high energy. And then the height of the line, you've got two different lines here, the height of the line represents the number of molecules. So when we've got a really high point on the line, we've got a lot of molecules at that temperature, or at that energy. Energy and temperature are interrelated. But we've got a lot of molecules at that energy. We're looking at actually two different temperatures here. So one distribution, we've got T1, that's in the blue here. We've got a lot of our molecules are kind of in this sort of region of the graph. The area under the line shows us how many molecules total we have there. So over on the left side with our blue line, most of our molecules are in this lower energy zone. So most molecules at low energy. But notice we do have this like front tail. I don't know a good word for front tail because tail kind of implies behind, but this is a front tail or a leading tail. So even though we've generally got low energy, we do still have some molecules that are at high energy. And this E, this line represents the amount of energy that we need to evaporate. So even though we're at a lower temperature, we've got most of our molecules at low energy, we still have some that are at higher energy, have enough that they can evaporate. When we bump up the temperature to T2 here in red, because red obviously is hotter than blue, right now we can see that our peak has shifted. It's shifted from being low energy to slightly higher energy. Our distribution has kind of widened out, it's flattened out a little bit. And now most of our molecules are kind of in this zone. We've increased the temperature, that increases the average energy. And now look, we've got this extra bit of energy, or this extra bit of molecules that now have extra energy and can evaporate. So we've got more molecules that can evaporate, but at both temperatures, this is the takeaway, at both temperatures, low temperature, high temperature, any temperature, you're going to have some molecules that have enough energy to escape. Always with a little asterisk, some molecules with enough energy to evaporate. This graph also works to describe what we were talking about with sublimation, where if you've got two different temperatures, a higher temperature, right, we've got some molecules that can sublime. They can go out of the solid state into the gas state. If you lower the temperature, we change the amount of molecules that have that much energy. We've decreased the amount of molecules, so we lower the rate of sublimation, and our food stays good for longer in our freezer. Questions about one of my favorite graphs? If you're having a little trouble keeping up, it's not a big deal. Don't worry about it too much. Remember, this is being recorded. You'll hear this if you come back and listen to it, so that's fun. A little inception there. And also, we've got Logan, who's got SI sessions and would love to explain all of this to you again, possibly in more detail, and definitely would be happy to do so at a slower rate and with less non sequiturs than me. On the other side of evaporation, we also have condensation. So evaporation was going from a liquid to a gas. Condensation is going from a gas to a liquid. Think of morning dew with condensation. So condensation is gas going to a liquid. Again, a lot of this is really good flashcard material. Go buy some 3x5 cards. Right on one side, condensation. Right on the other side, gas, arrow, liquid. Maybe write some fun facts about condensation in there too, if you can find them. So evaporation and condensation are opposite processes, since evaporation was liquid to the gas. We've got a special state when these rates are equal. So rates, how much is condensing and how much is evaporating. If we've got liquid going into the gas phase at the same rate, same number of molecules per second as the gas is going into the liquid state, that is dynamic equilibrium. So the dynamic part means that there is movement. Right, we've got liquid going into gas, we've also got gas going to liquid. We'll represent these processes by the size of the arrow. They're the same size arrow, right? So there's some moving in both directions. It took me a while to get the arrows going opposite directions. And the equilibrium part means that the arrows are the same size. The processes are happening at the same speed. And when we're in dynamic equilibrium, we are changing from a liquid to a gas and a gas to a liquid, but because the rates are the same, the amount of gas that's above the liquid will remain constant. And when we've got that gas is going to have some pressure associated with it, and we've got this special term, vapor pressure. Vapor pressure is partial pressure, so the pressure of that component. Pressure of the gas / vapor. And what's special about vapor pressure is that it's at dynamic equilibrium. So it's not just the partial pressure of the vapor, it's specifically at dynamic equilibrium. So vapor pressure, we can affect vapor pressure in a couple of ways. We can increase vapor pressure by increasing temperature and by decreasing strength of intermolecular forces. This differs from our rate of evaporation that we saw earlier. So rate of evaporation also increases with surface area. Notice that we don't have surface area here. Surface area does not affect vapor pressure, and the reason that it doesn't affect vapor pressure is that increasing surface area, if you've got a larger area that you can evaporate from, you also have a larger area that you can condense to. So it affects both evaporation and condensation equally. So surface area does not affect vapor pressure. This dynamic equilibrium process is why if you leave a closed container of water, like one of those $1 water bottles that we've been talking about so many times, if you leave one of those out and you've had half of it, you'll see that there's water up on the sides, where there's just gas. That's because the water is evaporated from the main body of the liquid. It's condensed out on the sides and it just hasn't run down to rejoin the liquid again. Let's do a really bad job of sketching that out for you. The more I draw, the more it's evident that I'm not an art student. All right, there's the main body of our water. Up here we've got just air. Arrow, water. But you also get little water drops that form on the sides. And then sometimes those run down into the water again. They could also evaporate back out. And here's some more diagrams. So we've got 3 different scenarios here to show our dynamic equilibrium. Initially, we've just got water. It's like you took one of those water bottles, you drank half of it or most of it, and now you've just got the water. and the top is mostly just regular air. So your sealed container, evaporation starts. Some of these water molecules leave the liquid state. They're in that high energy tail on that graph that we were talking about. That process continues, and eventually some of these water vapor molecules will hit the sides. They'll condense into water drops. Or they'll come back down and hit the surface of the water and turn back into liquid water, join the liquid water. And then at some point, the rates of evaporation and condensation are equal. And this state is relatively stable. So if we took another snapshot, if more time passed and we took another snapshot, it would look like the same number of particles up in the gas phase. They would just have moved around to different areas instead. All right, and then more practical applications of what we're learning. Because we learned eat your ice cream, which is a practical application. Another practical application, I'm going to go back a little bit here. Rate of evaporation, rate of vaporization increases with increasing area, increasing surface area, increasing temperature. We can practically apply this when drying our hands in the bathroom with the blow dryers. So obviously, one of the important points, increasing temperature. When the air that's coming out of the blow dryer is cold, it's not really helping evaporate the water off your hands very much. However, a lot of us probably are not taking advantage of increasing surface area. So there's a phenomenon that you will have seen if you've watched what I would consider a regular high school basketball game, or lower than high school. Right, you've got a bunch of sweaty players out on the basketball court. One of them, inevitably, usually somebody falls down at some point. And they slide and they spread their sweat all over the basketball court. And now there's water on the court. What do all the basketball players do next? Does anyone know? They all go around the spot where the person fell down and they kick their feet on the ground. Why are they doing that? Is it to show disrespect for the person that fell down? Are they saying, we decry you, you're the worst, why did you fall down, that's pretty lame of you? No, they're kicking the ground where the person fell down because there's water there, right? And that's going to be slippery. If somebody runs over again, it's basically a cartoon banana peel and somebody else is going to go down too. And then they might hit their head and that's a whole bad thing. So they're coming over and they're kicking the ground because basketball shoes tend to be grippy. And so when you're kicking the ground, that's producing friction. That's going to heat up the area. It's also going to spread some of that sweat onto their shoes. And so then they're increasing the surface area as well. And so that whole area dries up more quickly. The reason that I say regular high school basketball game is that at professional games, they just have a guy with a mop that goes out and mops the area down, and then it's magically dry. It's just like a giant towel. So when you are washing your hands, when you're done washing your hands, and you go and use the blow dryer, assuming there's no hand towels, right? Instead of just sticking your hands into that blasting warm air and waiting for 5 minutes for your hands to dry out, if you just rub them while they're drying out, spread the water around your hands, increase the surface area, and you can have your hands dry in a relatively fast period of time, and then you're not leaving the bathroom wiping your hands on your shirt or your pants or your clothes because they didn't dry out. So think about it. Try it next time that you go into a bathroom that has not one of the Dyson Airblade hand blowers, but any of the other ones. And you might be surprised at how quickly they dry out by taking advantage of increasing surface area. Okay, more fun. Boiling point. The boiling point is the temperature at which the vapor pressure, the partial pressure of the gas in dynamic equilibrium of a liquid is equal to the pressure above it. equal to the pressure above it. Where is the pressure?
Above it.
Above it. The pressure is above it, and it's equal to the pressure above it. There's a question that I like to put on exams that's about boiling point. I'll probably put it on your exam too. So what's happening at the boiling point, the temperature that our water boils or our liquid boils, our thermal energy, the energy of our molecules, it gets high enough that water molecules in the interior of the liquid, like underneath the surface, not just at the surface, we're no longer just that, like the little steam coming off your water. Now molecules on the inside have enough energy that they can kind of push away all their neighbors and, waving their hands furiously, leaving the rest of the water. They can become gases even on the inside as gaseous water molecules. And so you'll see bubbles coming out when your water is boiling. So evaporation is just happening on the surface. With boiling, we are also having that happen from the inside of the water. Usually when you're boiling a pot of water, you see it coming up from the bottom because that's where the energy is being input. Another application of this, because boiling point is when the vapor pressure of the liquid is equal to the pressure above it. If you change the pressure above it, that changes the boiling point. Pressure and boiling point are related. Increasing pressure increases boiling point. So if you've ever used a pressure cooker, I can't remember the name of the very popular pressure cooker brand. There's the one pot? Instant Pot. Instant Pot. If you've ever used an Instant Pot, those are pressure cookers. And what they do is they just trap the pressure in the container and you basically make a pressure bomb. But it's contained, it's not intended to explode. And so the pressure increases, and when the pressure increases, the boiling point of your water increases, and so you can heat your water up past 100 degrees Celsius. And since you can heat your water up above 100 degrees Celsius, you can cook your food faster. The opposite is also true. At lower pressure, like at higher elevation, pressure is lower at higher elevation. So if you go up into the mountains, like if you're at the Mile High City, Denver, or if you're even further up in the mountains, your boiling point is going to be lower at higher elevation. What this means practically is pasta will cook slower, or soups or stews or anything else that's cooking in water is going to cook slower because the temperature is lower. Some boxes of pasta, especially if you get like Patagonia provisions or fancy stuff that's like intended for going out into the mountains, it'll have some instructions on there for like if you're at 5,000 feet, then you want to cook it for an extra 2 minutes. Or if you're at 10,000 feet, you want to cook it for an extra 4 minutes. It'll include some information in there about how long you're supposed to cook it at higher elevation as well. We have the benefit of being at relatively close to 1 atmosphere of pressure since we're relatively close to sea level. So the directions on the pasta box is what we do, which is cool. And here's why. So once the boiling point of a liquid is reached, just like the melting point with our ice water, remember that very consistent ice water experience, the same thing is true for boiling water. Once you reach the boiling point of a liquid, additional heating only causes more rapid boiling. The temperature locks in at about 100 degrees Celsius. You will never boil a pot of water above 100 degrees Celsius if you are only using atmospheric pressure. It maxes out at 100 degrees Celsius. What this also means is that when you've got your water at boiling point, when it's boiling, you know that it's at 100 degrees Celsius or really close to it. So you add your pasta in, you know your water is at 100 degrees Celsius, you set a timer, it always cooks for the same amount of time. That's the magic of heating your water up to boiling to cook it. It's only after the water has all been converted to steam, you've boiled your pot dry, that the temperature of the steam can go beyond 100 degrees Celsius. So if you've ever wondered, why don't we check the temperature of our water when we cook pasta? This is why. You know that it's at about 100 degrees Celsius. It might be a little lower, a little higher, depending on where you are. Probably a little lower. So you might add just a tiny little bit of time to get the consistency that you want for your pasta. Another note about this, because I don't remember if it's somewhere later. I think it's maybe in a future chapter. When you boil water, there's usually some little bubbles before you start boiling your water, and you're like, oh great, my water is boiling. And then it's like 5 minutes later, and you're like, my water isn't boiling yet. Those little bubbles, which I think, again, we'll talk about later, little bubbles before boiling are dissolved gas leaving. So that does mean that you're getting closer to your boiling point, but it doesn't mean that you're quite to your boiling point. Wait for those weird shaped bubbles, the big bubbles, to come out to know that you're at boiling. Any questions? All right, we'll stop there.